Ian, and this video is in response to some comments I've been pitching back and forth with a guy by the name of Massimiliano del Guzzo. Quite the name you've got there. Anyway, so this was the comment I wanted to consider. I did actually go through this comment last night, and I was a bit drunk. I had 4 ciders. I didn't make too much sense of it. I kind of got the general gist of it, I think. Namely, we have like, I think what I'm going to do, I'm going to present the argument in a nice way, and then I'm going to try and relate it back to your comment, just to show you how things play out with regards to events and length contraction, time dilation, simultaneity. All of that gets jumbled up in this, I think, in the context you were considering here. And you ended up on some kind of conclusion that the Earth is moving, appears to be moving, faster in one frame than the other, or something along those lines. I couldn't quite make sense of it, to be honest. If there was, just by virtue of the fact that the Lorentz transformations are, forward and backwards are pretty much the same, other than a change in sign of the velocity, that I can't see how that would happen at all, to be honest. All of that phenomena, which is, in my experience, there are different ways of learning special relativity. One of them is to learn kind of the main effects first. So that's the way I learned it. I learned about length contraction and time dilation. And then I learned about this so-called rear clock ahead effect thing, right? That's basically jumbling up the simultaneity. And you can do it that way without drawing space-time diagrams. But honestly, it's a heck of a lot easier just drawing out the diagrams and seeing it all happening. Because, yeah. Well, let's go over it, okay? So I think, what we had here, you were saying we had the point negative D0 in this frame. I'm going to call this the prime frame, okay, so F1. And then you're saying there's a point D0 in the frame F. Okay, so that's, so you have some symmetry going on there. Let's just get that down and see what happens. So we have an unprimed frame and a prime frame. All right, so, and then we can go ahead and do this. So this is my unprimed. I'm going to need a bit of time below, I think, depending on things. And you were saying, so this is unprime, and then you have prime frame. And the prime frame is moving at speed v towards the right. Typically how it's done, right? So, and the origins are coincident. So this is x prime, t prime. This is t and this is x. And the origins are coincident. So this event here, let me call it the event O for the origin. This is the same event here. So the event O, you could summarize as, x equals 0, t equals 0, and vice versa. The x prime and the t prime is 0 as well. So that's the event O. All right. So, and then you're saying there's a point negative D0 in the f prime frame. So let's go ahead and draw that. So that's going to be this guy, right? So that's negative D, and you're saying that's a point. And I think you were considering like the world line of that point, weren't you? So if you consider the world line of that point where the x prime is stationary in that frame, then it's going to be looking a bit like this, obviously. And we could call this, let me call this the event, let's just label that the event A, right? So this is the event A. We can go ahead and talk about the event A. So the event A, obviously we know what the prime coordinates are. X prime is negative D, and the t prime is the 0 at the moment. But what are the x and the t? And this is where I'm going to go ahead and just calculate things on another page. So, and this is just using, again, the Lorentz transformations. So we had the x prime equals the gamma x minus vt. and likewise t prime equals the gamma, and then t minus vx, isn't it? Yep. Very nice. Keep using curly x's, right? So that's what you might call the forward transformation. Likewise, the reverse transformation is pretty much the same. Well, it is the same other than the change in the sign of the, the velocity. So x prime plus the vt prime, and likewise we have the t prime plus the vx prime. Right, very nice. So that's that one, right? Forward and reverse transformations. And we have this coordinate negative d0. You can chuck in those right here. And the x itself for the coordinate of d would be, well, it's going to be x equal gamma, and then the x prime is negative d, so you get negative d. The t prime is 0, so you just get negative gamma d. And then you have to bear in mind the fact that the gamma is this guy, the root 1 minus v squared reciprocal, and that's always going to be greater than the 1. Have I done that right? Yeah, that's correct. That is correct. You'll see why in a second. So that's greater than the 1. Let's go ahead and calculate the t for this guy, and it's not going to be 0, is it? Because that event actually gets shifted a little bit in time because it's offset from the origin of the prime frame. So, and that's quite an important consideration when you're doing this kind of stuff. So I'll talk about the length contraction idea in a second, but let's just go ahead and do the calculations here. So t is going to be the gamma, and then the t prime. What was that? That was a 0, isn't it? And then the vx, the x prime here was the negative d, so you get the negative v d. So you get, this funny negative gamma vd like that. So that is the event A in the unprime, negative gamma d, and negative gamma vd, which seems kind of weird, right? But it does check out. So the time is now negative, so it's going to be down here, right? Yeah, so this is negative gamma d right there, and this is the negative gamma vd. So that's the event A. So you can do this kind of stuff. And I think another useful thing to recognize is, these events are getting shifted around on the hyperbola because the space-time interval, the delta x squared minus the delta t squared. Remember, this is a constant regardless of which frame you go to. So the space-time interval between the event the origin event and the A event is always going to be the same. And lines where this thing is constant actually form hyperbolas, and that's why space-time. That's why that's what we call it a hyperbolic geometry. But it's a geometry which involves both space and time. So so you can imagine a line. They look a bit like this hyperbolas. So if I just draw them off on another slide here, they look a bit like this. Go down, go across. That way, and that way. They look a bit like this, right? Depending on things. So that's and then you have like a line of you have an asymptote like that. I haven't drawn them very well. You get the idea. And then you have another asymptote like that. So now when you're dealing with the space-time geometry, these are going to be perfectly 45 degrees. So the asymptotes will be the the light-like rays from the origin. So you can imagine. I know I'm getting a bit off topic here, but I think it pays just to help visualize this. So you can imagine the asymptotes for the hyperbola here, like that, like that, kind of like that, and then you have the hyperbola passing through that one. So it's going to be looking a bit like this, like that. And in going from the prime frame to the unprime frame, this event of A, as I was calling it, let me circle that A. Yeah, I'll circle the origin as well, just to stick to the convention like that. This event of A is actually being kind of shifted down here when you go from the prime to the unprime, And here we have this prime frame moving at speed v towards the right. Okay, so and that the event A is now down here. Okay, so that makes a lot of sense when you think about it. So, and you can imagine what's going to happen when you look at other events. When you can kind of picture what's going to happen when you look at it like that. So, I don't know what else you were saying. You were saying the point Q d0 of the frame F reaches the origin. Okay, so let's do the world line of this D, right? So this D, because it's constant in the prime frame, it's going to be moving at speed v. So the world line is going to be a positive v gradient in this frame, right? So it's going to be that world line of the event negative D is going to be doing this kind of thing, like that. And I think what you're talking about is when it hits the origin of the unprime frame, aren't you? So that's when, oops. That's when, well, that's going to be this point here. Let me call that the event of B. And we can imagine where that's going to happen over in the prime frame. So in the prime frame, the origin of the unprime is going to be moving towards the left with speed V. So here's the world line of that event negative D. If I could get straight lines happening. All right. And then it's going to be, let me do the world line of this frame in yellow. So here's the world line of the origin, obviously just moving up on the time axis, right? And over here it's going to be kind of shifting off at it's going to be shifting off at a speed v towards the left, kind of like that. So that's going to be the world line of the, of the unprime frame moving towards it. And that's going to have a pretty simple form. It's just going to be a gradient of negative v. So it's going to be the x prime equals the negative vt, right? In this frame. Over in this frame, it's pretty easy. Just x equals 0, right? The equation of that line. And this event here, that's going to be the event of b, right? That one there. And yeah, we could calculate the space-time coordinates of b as well if we really wanted. It's not difficult. So, and again, there are many ways of doing that. So over in the prime frame, you have the x prime, t prime. Let's calculate. X prime is going to be negative v. Well, we know the x prime is negative d here, don't we? And then the t prime is going to be just that divided by negative v. So it's going to be just d over v naturally, right? Nothing's funny going on here. It's all expected results. And then the x is obviously 0 in the other frame, and the t. What is that? Good question. That's going to be the proper time, isn't it, between the events O and B, because the events O and B have 0 spatial separation. So that's going to be the proper time. It's going to be the shortest time between those two events. So we expect it to be, well, it's going to be the original. I expect it to be this thing divided by gamma, yeah, because it is the proper time. So it's going to be the d on v and then divided by gamma. So let me just write that as t prime on gamma. But if you wanted, you could also prove that just using the, using the Lorentz transformations. So you can take this funny thing here. You can plop it into these Lorentz transformations here. Let me just glue these together. Hang on. Move that one down a bit. All right, so there's my event B down there. Glue them together. This was the event of A, wasn't it? Was it? I was calling that A. Negative gamma D. Yeah, I was calling that A. All right. That's A. This is B. All right. And I was finding the coordinate of T. So yeah, we can do that. Just to show you, it's going to be the proper times. So T, this guy, right? So gamma, and then the T prime is D on V, and then plus V x prime. The x prime is negative D, so you get minus V D in that fashion, close. And then I want to write that purely in terms of the original time. So that means factoring out. I think I want to factor out a factor of V there, don't I? So is that what I want to do? Yeah, let's do that. So you factor out a factor v, you get gamma v, and then you get the d on v squared, and you get minus d here. So I guess you could put out the factor d as well, can you? Factor d, and then you get the 1 over v squared minus 1, which is the same as 1 minus v squared all over v squared, right? And then that 1 minus v squared is going to cancel with the gamma here. So, and also the v squared here cancels. So v on v squared is 1 over v, right? And then you get the d on v, so that's my original time, t prime. And then you get the gamma times this 1 minus v squared. That actually turns out to be 1 over gamma when you do the math. So there you go. You just get the original t prime divided by the gamma, right? It's the proper time. It's the shortest time. It's the time which is moving with respect to those events. It's the time in the frame of reference which is moving with respect to those events. So that's the one with the spatial separation. That's the prime frame. This one here, right? So OB has a spatial separation. And then the time in the unprime frame is just that thing divided by gamma. So that's your usual, that's where time dilation comes from, right? But you can see it very clearly here. You don't need to, all you need is the Lorentz transformations and some space-time diagrams. That's all you need. And it all just makes sense. Anyway. All right, I'm going to pause this one and I'm going to take a breath and think about what I'm going to say next. Look at your comment, and I think you're saying we want to imagine a spaceship in the prime frame. And I think that spaceship was a length d is what you're saying, isn't it? Yeah, tail is d. The length of the tail is d. Imagine a spaceship has a tail, and the length of the tail is d in the frame of the spaceship. At the end of the tail, okay. All right, so you're imagining a spaceship in the prime frame of reference. And I think you were going to imagine that moving towards the, yeah, all right, so let's kind of draw that on. So here's the world line of the spaceship, right? This represents all points on the spaceship. I think that's what you're saying, isn't it? And then you're saying at the end of the tail is John. So that's going to be this world line. So John is on this world line. I think that's what you're saying, isn't it? And then the twin on the Earth. So the Earth is the unprime. And so the Earth is located at the yellow world line, right? So here's the Earth. And so the twin is going to be on this world line. I think that's what you're saying, isn't it? Is that what you're saying? That's the Earth. And you're saying the twin on the Earth sees John at a time t equals d on gamma v. The twin on the at time t equals the twin on the Earth sees John. Okay. Yeah. Okay. So we could imagine the light ray from John. I guess if John spontaneously combusts into existence right here, then you can imagine the world line. That's going to be this event down here, by the way, for the event A there. So if you have John combusting into existence here, he's going to be combusting into existence here. So that's the point of content. That's going to be, again, that's not very clear how you worded it. But it's pretty easy to do the maths if you wanted in the prime frame. So you could do a 45-degree out from there. There's your world. That's the light world line. If John was to combust into existence here, and then just do the intersection of the two lines. Pretty easy, right? This line is x prime equals the negative d, and then plus t, and then you just simultaneously solve with this equation, and you're going to get the t prime, right, as well as the x prime. So that's easy. So let me just do the algebra. So you get negative v t prime equals the negative d plus t prime. Then you add it all over, so you get d on this side, and over here you get 1 plus v, so you want to divide by the 1 plus v there, and that's going to be your t prime for that one. D, is that correct? Yeah, that's all looking good. Yeah, that's looking fine to me. And then obviously you could find the x prime there as well. X prime would just be the negative v times t prime, so it's going to be this thing times by negative v, so you get negative dv on 1 plus v. So that's your space-time coordinates for this event. Again, we need another letter now, but that's not really. And then you can ask, what would that look like over here? Let's give it a letter. Okay, let's call it the event C, perhaps. And over here, we have the world line of the light ray. Again, it's going to be 45 degrees, so it's going to be looking about like this, kind of like that. Moving off from the spontaneous combustion of John. And then this event here is going to be the event C in this frame of reference. And you can do this kind of stuff all day. You can do this kind of stuff all day. And the event C here, well, obviously the x equals 0, right? But what about the t? Good question. I guess you could find the t by using the reverse transformation, so it's going to be the gamma. Remember what it was? It's the t prime, so it's going to be d on top of the 1 plus v, and then it's going to be minus the vx, so that's going to be plus dv on 1 plus v, so that's my x, and then it was minus v times that, so that's going to be v squared on top, and then close, and that one's going to tidy up because when you factor the d as well as, again, I don't want to make too much mess on this whiteboard. You get the gamma d, you get the 1 plus v, and then you get the 1 plus v squared, don't you? Coming out. Is that correct? Yeah, I think that's correct. Yeah, so that would be the time of that then in that frame. I don't think that's what you were getting at. Again, it's not immediately clear how you've worded it. You're saying the twin sees John, or the twin's going to see John when the light reaches the twin, and that's the event I've calculated. So I'm not going to follow that line of reasoning any further because it's not very clear. I'm just going to get rid of all that because I'm not particularly interested in it. So you're saying spaceship with the tail and the f-star distance. So the star, that's well, you're saying the star is point Q, and the point Q was D0 in the frame F. Yeah, so that's okay, right? So you're saying, yeah, you have to appreciate. You're now saying the star is the distance of D in the frame F. So here's D, right? And then you can do the word line on that. So here's the star word line. Running out of colors now, aren't I? That's green, isn't it? Maybe blue. Here's the world line of this star. Okay, looking about that. And then you have to ask what that's going to look like in, I'm just going to get rid of this. It's getting in the way. You have to ask what that's going to look like in the prime frame, right? So because the prime frame is moving towards the right, this world line of the star is going to be moving towards the left with a speed of v. So, well, that's yeah. So, yeah. So again, you can calculate the coordinates, but you need to label the events as you go along, right? Again, you can imagine the hyperbola on this frame, the unprime frame is going to be looking about like this, the hyperbola passing through that. And that event is going to get moved about on that hyperbola when you go from the unprime to the prime. And I think this time, because you're going from the unprime to the prime, it's going to get moved kind of up on the hyperbola. So that the event here, I haven't labeled it. Let me label it C again. So the event right here would kind of get moved upwards and around to the event right here when you go to the unprime frame. Sorry, when you go to the prime frame. And again, you can calculate all that. It's pretty much just what I've done before. But again, just to spell it out, let's go ahead and do that. So I was calling that the event C now. And that was the x equal d and the t equals 0. So the x prime is the gamma, and then the x minus vt. So the x is d minus vt, so it's going to be 0. So again, you get the gamma d, and then the t prime this time is going to be the gamma times with t, which is 0, and then minus the, is it minus the x? Yeah, minus the v x, so it's going to be minus v d, so you get the negative gamma v d, and likewise you get the gamma d for the x prime. That all looks fine to me, so same results. I just want to make sure I got the negative correct there. So that was going, yeah, minus is when you're doing the forward transformation. Yep. And then, yeah, okay. That's looking at it. So this event is actually going to move down. Yeah, it actually moves down when you go from, yeah, so it's moving down. It's going to come down here like that. And it's over here, it's going to have, it's going to be, well, it's going to look pretty much the same as it's going to be the gamma d on the x prime, like that, right there, and it's going to be the negative gamma vd on the t prime. Okay, so we have some nice symmetry here, right? I guess another thing we could draw in is the world line of the spaceship. So this is all the points which exist on the spaceship, I think is what you're saying, isn't it? I think that's what you're saying anyway. So all those, that's going to be a continuum of events. So this is the front of the spaceship, and it's going to be the world line at the front of the spaceship would be that line there, and the world line at the back of the spaceship would be that line there, which is just what we're calling John, right? But also all these points in here would exist on the spaceship as well. So just in the intermediary of the spaceship, right? So that's, yeah. So the space-time events which represent the entirety of the spaceship actually form a 2D plane in the space-time diagram. All right, very nice way of looking at it. And we had this point here, that was the star, right? The event C, this world line, I was doing that in blue, but that's now going to be moving backwards at speed v. So it's going to be parallel to the yellow here, the twin on the Earth, but it's going to be passing through that point like that and parallel to the yellow. So that's the world line of the star, as you're calling it. And you can see it is going to hit this spaceship at some point, which is, I think that's what you kind of talk about a bit further on in your comment, don't you? But we are definitely getting somewhere here. You just have to be quite careful about how you think about things, right? Because this stuff is, I mean, when you first see it, it's not intuitive at all, right? So the blue is the star. This is the star. All right. So, yeah. All right. Take a pause. Next video. I wanted to focus on this little bit here. So you're saying the spaceship with the tail and the Earth star distance are two distances in relative motion. Certainly true. Speed v, and you're saying they overlap. They are two distances have both have a length d in two different frames. Okay, let's just analyze that statement with regards to the spaceship and the world lines. So I haven't done the world lines of the spaceship in the unprime framework, so let's go ahead and do that. It's a little bit tricky, I suppose, because this spaceship, if you imagine the spaceship being all these space-time events here in the prime frame, then it's actually going to constitute all these space-time events here in the in the unprime frame. So you can see how, but that's what you wouldn't perhaps say is the spaceship at that time in the unprime frame, because obviously, when you're talking about objects, you have a continuum of space-time events, and when we talk about the length of an object, we're talking about the space. We're talking about the spatial separation of the space-time events, which are considered simultaneous within that given frame. But you can clearly see when you go to the unprime frame, the events which are considered simultaneous change, right? This event A is no longer simultaneous with the event O. So if you wanted to calculate the effective length of the spaceship in the unprime frame, you'd have to consider this event here, and this is what you would say is the length of the spaceship in this frame, right? Really important. And that one's going to be length contracted, right? Because we've heard about this idea of length contraction, this distance here I know is going to be d divided by gamma. That is length contraction when you look at it from the perspective of space-time diagrams. It's not too difficult to calculate that as a coordinate, right? We know, for example, the equation of this curve is going to be x equals well, I guess, yeah, you could just use straight line geometry to do it. You can just say x minus gamma, so yeah, so x plus gamma d equals, and then this line is a speed v, isn't it? Because it's the spaceship moving at speed v, so it's going to be vt, and then don't forget to do t minus, well, plus the gamma vd, like that. And that would be the equation of that line. And then you can just set the t equal to 0, and that's going to solve you for the x there. So when t equals 0, you get the x equals, you get the gamma d, you get the negative gamma d coming over. I guess we could factor that. So gamma d factor, and then inside here you get the v squared, and then minus the 1, like that. Which you could also write as negative gamma negative d, right? And then you get the 1 minus v squared, and then that becomes 1 over gamma, right? Because yeah, so you get the x coordinate is negative d over gamma for this point here. Let me call that the point D, just to make it clear, right? So this is a space-time at D, and it has the coordinates of negative d over gamma. That's x equals, and likewise the t equals 0, right? So that's that one. I'm just going to delete all the workings there because they're getting in the way. All right, so the spaceship is going to be length contracted in the Earth's frame of reference, right? And then the continuum of points which represent the spaceship, again, it's going to form like a 2D plane when you shade it in, except it's just going to be, this kind of 2D plane here, looking a bit like this, as I've drawn it, right? So that's the back of the spaceship right there. This is the front of the spaceship right here, and here's the 2D plane representing the spaceship, kind of like that. All of that stuff, right? And also down here as well, if you include this little bit down here. So, all right, so that you can see it's all getting transformed out in the way I expect. And then what you were saying, the two distances in relative motion to each other at speed v, and they overlap. Yeah, again, you have to be very careful about when you use the word overlap, because again, the events which are simultaneous change as you go from one frame to the next. To say they overlap in one frame at a particular time doesn't necessarily mean they overlap. Yeah, so let's analyze that statement. Okay, so we had the star, right? And the star was this line here, like that. You're saying the Earth star distance, which is the O to D, the event O to the event C, except the event C was down here for this space-time, wasn't it? So you're saying this OC overlaps with the spaceship. Yeah, again, I guess you're going to get symmetric results here, aren't you? So here the length to the star was D in the unprime frame. But when you go to the prime frame, it's going to be a length of D divided by gamma. So again, the simultaneity kicks in there. This event here is not the same as the event C. I'm going to call it the event let's call it the event D, right? And the event D is going to have, I'm using D up here, aren't I? Where was I using that? I was using that. Negative D. Oh, I was using it here, wasn't I? I was calling that D. Let's use the event E. All right. So the event, let's call this event E. And E is going to be very similar to D, isn't it? So E is going to be it's going to be the D divided by gamma. X prime is the D divided by gamma, like that. And the T prime is going to be the 0, right? But it's not the same as the event D. So, all right. So that's what's going on, right? I think I've followed you so far. And then you're saying the Earth reaches the point P, and the point P was the negative D0 of the prime frame. So that's the back of the spaceship, and you're saying that meets, yeah, so that's, you're focusing on this point here. All right, yeah. And then you're calling that A. I've called it something different. I think I called it the event B, didn't I? Yeah, I called it the event B. And then the point R reaches the spaceship. The point R is D on gamma, comma 0 in the frame of the Earth. In the frame of the Earth, D on gamma. We don't have that yet. And then consider okay, so you're saying D on gamma for some reason. That's going to be kind of here-ish, isn't it? Right? D on gamma. Like that. Doesn't represent the star, it represents D on gamma in the frame of the Earth. Is that what you're saying? Imagine the point R, D on gamma of the frame of the Earth. I can say that. Point R reaches the spaceship. So this is R as you're calling it, and it reaches the spaceship. That's going to be this guy here. Yep. The two events A and B are simultaneous in the frame of the Earth. Is that true? Is that true? Okay, yeah, I think that is true because it's D on gamma there, and then it's D on gamma there, so that moves off. D on gamma forward, yeah. Okay, yeah. Oh, okay, I'm with you so far. So the little green thing I just did and the little white thing I just did are simultaneous. That's what you're saying, right? In the Earth, right? So it's two events A, B, so the point P reaches the Earth in time D on gamma V. Yeah, that makes sense. You got a distance D on gamma divided by V, yep. And the spaceship, yeah, and yep, that all makes sense to me. In the frame of the Earth, the length of the tau is contracted. Yep, that's the D on gamma, yep. If the spaceship has a distance equal to D on gamma, if the spaceship travels a distance equal to D on gamma, the twin on the Earth sees John. All right, so that's when John is on the back of the spaceship, and yeah, so this is when John sees the twin at the event B, isn't it? And the events A and B are not simultaneous in the frame of the spaceship. Yeah, it's going to be true. So I haven't drawn that over here, have I? So if you got the green dashed line is going to be well, this was the d on gamma. So over here it's now going to be d on gamma squared, isn't it? For your dashed green line, and it's going to be moving off towards the left, kind of like this now. So that's what you're saying, isn't it? And then this is when that hits the spaceship. And then when the yellow hits the back, that's going to be the event B right there. And you can see just eyeballing it that the green is not simultaneous to the white. Yeah, certainly true, right? And then I think you're calculating the times, aren't you? So D on gamma squared V. Yeah, that makes sense. You're just dividing that distance by V. Yeah, that's going to be the time. And then the time here is going to be D on gamma V. Yeah, that's going to be, yeah, that makes sense to me. So this is D on gamma V. This is D on gamma squared V, right, for the time. Yeah, makes sense. And then now consider C, point C, Q, point Q reaches the spaceship. So point Q was the star, and you're saying when it reaches the spaceship, that's going to be up here. This guy, right? That's what you're considering. So you're calling that the point C, yep. And over here, that's going to be this guy right here, isn't it? Yep. And then you're saying in the frame of the Earth, the spaceship reaches point Q in time t equals d on v. Does that make, yeah, d divided by 8, yep. So distance d divided by v, yeah, makes sense. And then in the frame of the spaceship, the point Q reaches the spaceship in a time t equals d on gamma v. Let's make sense of that. So yeah, this event E was d on gamma, so you do d, you do that one divided by v, and you're going to get that time. Yeah, so d on gamma v. Yeah. If we know that the spaceship moves uniform rectangle in the frame of the Earth, then the point Q, which is the star, reaches the spaceship at time t prime equals d on gamma v. Yeah, we just said that. And the Earth also reaches the point P. That was this this funny thing here, right? The back of the spaceship, I think, wasn't it? At a time t prime equals d on gamma v. T prime equals d on gamma v. Yeah, that's just the event B, isn't it? Yeah. Okay, all right. What's your point then? So the motion of the Earth is in advance of the uniform rectilinear motion or in the frame F prime. X prime equals negative V T prime. So that's the Earth, yeah. X prime equals negative V T prime, yeah. The Earth moves negative with speed negative V times gamma. I'm a bit confuzzled there. So you got a distance of d. And you're saying when the Earth meets the back of the spaceship, yeah, it's d on gamma v. Yeah, I see what you're saying. So this space-time coordinate of b is a distance of d, but we calculate a time to be d on gamma v. Yeah. Where did that time come from then? It came from doing point reaches this. just looking back at your logic, I think these ones are correct. So you're saying time equals d on gamma v for this point here, right? Because you have, so you were saying this is the point R, the green line, d on gamma. This is a line of speed v for the star. So sorry, for the front of the spaceship, and it's going to hit that point R at the time of d on gamma v. Makes sense to me. And then this distance from O to C is when you do go to the unprime frame, it's going to be contracted. But again, it's going to be contracted, so it's going to be d on gamma squared, that distance, and then that's going to be d on gamma squared. Yeah, that's fine. Yep, that's looking good. I think this one went a bit wrong though. So the d on gamma v, where was the logic for that? You were saying this event here, which I'm calling the event of B, is it has an x coordinate of 0, and the time coordinate we were saying is, well, it would just be d on gamma v. It's going to be the contracted length distance of the spaceship, and then divided by v. So it's going to be time of d on gamma v for that one, right? And likewise for the green as well. That makes sense. But then right here, you're saying the events A and B are not simultaneous in the frame of the spaceship. The point R reaches the spaceship T prime equals D divided by gamma squared times V. Yeah, so that was this one here, the green. I'm not sure what bearing that has on the argument, to be honest. That's just some point, right? And they're not going to be simultaneous anymore either. And then you're saying the time T prime, the Earth reaches the point P, which was the back of the spaceship, I believe, wasn't it? Yeah, the back of the spaceship. You're saying it reaches the point P in a time T prime equals D on gamma V, which you set up here as well, didn't you? T prime equals D on gamma V. So why are we saying D on gamma V? That's the time of this event in the unprime frame, isn't it? Because you have a length contracted distance of D on gamma here. But over here you have a length of D. So the time here would be D on V for that event there. And again, I think I've already done the coordinate transformation for that, but I did it down here when I calculated it on the other page for B. That was down here, right? That was the calculation for the event B. So the T prime is D on V, and the speed of the Earth is just V, or negative V in the prime frame. So I think you've got that one wrong. T prime equals D on gamma V. I can't see where you got that from. And I can't see why I made the mistake talking through it, to be fair. I can't quite see the logic. You're saying point Q, which is point P negative D0 of the prime frame, reaches the origin of the frame F at time D on gamma V. You're saying negative D0 of the prime frame. Oh yeah, that was the back of the spaceship, wasn't it? Yeah. Okay, so you have the back of the spaceship. That's this world line here, and then that becomes this world line here. And then we're saying the back of the spaceship meets John at the D on gamma V. Yeah, okay. Whereas over here, this is the back of the spaceship. And then we're saying John meets the Earth at this time here. Yeah. Yeah, I see what you're saying. Yeah. So I think you haven't quite grasped the fact that the event A actually has a negative time in this frame. And that's why you're getting what appears to be an asymmetric result. The time from the event A to event V to the event B, you could calculate that in in the unprime frame, right? And that's going to be just that time, the d on gamma v plus this time, the gamma vd. So that'd be the time from the events A to B, which we could calculate. Let's just do it here, right? So if you're going to go from A to B, the accumulated time is the gamma vd plus the d on gamma v, right? That's what I'm saying. Or let's call it the delta t for the difference between the time in those two then. But the delta t prime for those two events, well, let's think about it. Is in the prime frame, the events A and B have a spatial separation of 0, so the time between them is going to be the proper time, and the proper time is just going to be well, it's going to be the shortest time, isn't it? So it's going to be the time as calculated here, but then divided by gamma, right? So you could just do it that way. And we should find it just comes out to be d on v, but let's just go ahead and check. So if you divide this whole thing by gamma, what do you get? What do you get? So this is what I'm saying. I'm saying that's delta t divided by gamma, which is the vd plus d on gamma squared v, like that. So again, you can factor a few things here. You can factor the v, you can factor the d, and then you get the 1 plus, you get 1 over gamma squared v squared, don't you? And then again, you can do things with that. So gamma squared v squared, what is that? That's just v squared over 1 minus v squared. So if you divide, what am I trying? I'm trying to get d on v, aren't I? I'm trying to get d on v, aren't I? Am I trying to get d on v? I'm trying to get d on v for the time, aren't I? Between A and B as the proper time between those two events. Yeah. So the gamma should cancel in some fashion. Yeah. All right, let's have a look. Gamma. So we have the reciprocal of that. Yeah, and then we have plus 1. I might need to factor that in. Okay. So let's just do that. Vd. And then you have this upside down, and then plus 1. So that's right, you have 1 minus v squared on v squared, and then plus 1. But adding 1 is the same as adding v squared on v squared. So when you pull those two together, the v squareds and the numerators cancel. You get 1 over v squared just left over. And the 1 over v squared cancels with the v to give you the d on the v. Right? So right? So that is the time, right? Between the events. Of A and B. So I think that solves your apparent kind of paradox, as it were. It's just the misalignment, you disregarded the fact that this event A gets pulled into the negative time when you transform it out to here. So this little point here constitutes a new event, and that's what I was calling the event D. And that's when the back of the spaceship is simultaneous with the front of the spaceship when the front of the spaceship passes through the origin. But that's not the same as this event here. This is the event A, which gets pulled down to here. Yeah, so I think that solves that one. This all works out fine when you do it properly. It just takes some thinking. Yeah. No, so the motion doesn't break the symmetry. You're just disregarding the fact that the simultaneity gets, jumbled with the event A there. So, all right, I think that solves that one. So I hope you enjoyed that. It was a nice intellectual exercise. I haven't played around with this stuff in a long time, to be honest. So it's nice to come back to it and make sure I can still do it. I might look at your next comment another time. But again, there's probably just some minor subtleties that you've overlooked with regards to, the times and things. If if this stuff did break, then it would have been picked up on a long time ago. All right, this is very, very well-grounded physics, and a beautiful kind of mathematical application as well. Like when you look at it this way, I never learned it like this when I first learned special relativity, and it's a big shame looking back. Like I would have understood it much better, and I would have done much better in my first year exams. But no, using space-time and colors and stuff, it just makes it a lot easier. So yeah, so hopefully that answers your comment.